Hi, thank you so much for watching. My name is Diego, and today we will review how to implement a Physics Informed DeepONet in Python. As always, this code will be available in my GitHub, and the link will be in the description of this video. Here, you will find a few more examples that could be useful to you if you're just starting in this field. We use DeepONets to approximate operators, but what's exactly an operator? And to answer that question, let's go back to what's a function. Well, a function, it's a mathematical structure that maps between vector spaces. For example, let's take the sign of x. If we input any real number, we will get a number between 0 and 1. In other words, a function takes a number and outputs another number. On the other hand, an operator maps between infinite dimensional function spaces. For example, let's take the derivative operator, and let's apply it to the same function, the sine of x. If we apply the derivative operator to the sine of x, well, the answer, the output would be a function that would be the cosine of x. In other words, an operator takes a function and transforms it into another function. But why do we want to study operators? To answer that question, let's go back to one of the previous tutorials where we solved the Burger's equation using a physics-informed neural network. We were given the diffusion coefficient, the domain, and the initial and boundary conditions. But what if we want to change the fluid? Well, then the diffusion coefficient would change, which would mean that we are essentially in a different problem, so we need another neural network. But wait, what if we just want to change the domain a little bit? Well, it would be a different problem, and we need another neural network. So, is there a way to solve the Burger's equation in a general way? I mean, where some parameters can change and I can still get the solution without the need of repeating the whole process? And the answer would be yes. And that's where operators come really handy. So let's recall that in a PDE, we usually have an input function, and that the solution of the PDE is also a function. So we could get an operator that takes the input function and outputs the solution of that partial differential equation. And that's basically what a DeepONet is meant to do. We know we want operators to solve PDEs in a general way. In other words, we need operators to solve parametric PDEs. But how to get those operators? Well, for that we have the universal approximation theorem for operators. Here, let's pay attention to this g of u of y. If we observe the output of an operator, it's a function, in this case g of u. And if we evaluate a function at any point, let's say y, well, then we would obtain a real number. And that's one fact that we will use to approximate any operator. And well, the universal approximation theorem states that we can approximate any operator if we choose the right parameters of these two functions. Please note the dot product between these two functions. Now, the nice thing about these functions is that if we look at them closely, they have the same structure as a neural network. In other words, we can approximate any operator by the dot product of two neural networks. And that's exactly what a DeepONet does. Now, let's define the DeepONet components. First, we have the branch network. And as we can see it right here, the branch network takes the input functions. It encodes the input functions. And also, we have a trunk network. And as we can see it right here, the trunk network takes these y points. These y points are several points sampled inside our input function domain. Now, let's recall that the output of an operator is a function, and if we evaluate a function into a set of numbers, we will get a set of numbers. So, our goal would be to approximate the solution of our partial differential equation evaluated at y using a DeepONet. And that is the condition that we will try to enforce using a loss function. What is a physics-informed DeepONet? Well, just like a physics-informed neural network, A physics-informed DeepONet, it's a DeepONet that follows the rules set by a partial differential equation. But how do we make it follow the rules of a partial differential equation? Well, we will take our partial differential equation and we will rearrange it in such a way that it equals to zero. In the same way that we would do for a physics-informed neural network, for example, here in the Burger's equation. Then we will enforce that condition into a loss function. Finally, the total loss for a physics-informed DeepONet would be the loss of our operator plus the loss of our partial differential equation. Let's use a physics-informed DeepONet to solve the diffusion reaction system represented as a partial differential equation. You can see that this partial differential equation is parameterized by the input function, also called source term u of x. We have some data on the domain. We have some data about the diffusion coefficient, the reaction rate, and the initial and boundary conditions. One of the main advantages of physics-informed machine learning is that it works pretty well when we do not have much data. For example, in this case, we only know that the solution of our partial differential equation at the initial and boundary conditions is zero. Our goal would be to approximate the solution of our partial differential equation for a specific u of x using a physics-informed DeepONet. To do that, first, we will rearrange our partial differential equation in such a way that it equals to zero. Then we will enforce that condition as a loss function. After that, we will sample several points from our initial and boundary conditions and evaluate our DeepONet on those points. Since the output function evaluated at the initial and boundary conditions is zero, the loss operator simplifies as follows. Finally, we will add the total loss of the partial differential equation plus the loss of our operator. So let's make a brief summary of what we want to do. First, let y equals to the input variables x and t. And also remember that for this example, u is only a function of x. So to train a physics-informed DeepONet to solve the diffusion reaction system, we would select n input functions, evaluate those n functions at m points, send the m outputs of our n functions to our branch network, select p points, which we will call output sensors from our boundary and our initial conditions, and let's call them yu. Send the output sensors to our trunk network. Approximate our operator by computing the dot product between the output of our branch network and the output of our trunk network. Ideally, our DeepONet applied to our initial and boundary conditions should approximate to the solution of our partial differential equation at our initial and boundary conditions, which we know it's zero. So compute the loss operator. Select a q points, which we'll call them collocation points inside our domain, and let's call them YR. Compute the error related to our partial differential equation on the collocation points. Compute the total loss. Update the neural network parameters, which the branch network and the trunk networks, to minimize the loss function. In this tutorial, we will use JAX for our machine learning tasks. Here the JAX APMap tool comes really handy to generate our input functions for our PDE. Remember that this partial differential equation is parameterized by the source term u of x, which means that we need to generate a lot of functions u of x to train our model. And well, JAX makes it a bit easier. If you're not familiar with JAX, please do not worry. You will see that it feels like a NumPy extension, so it's really friendly. Previously, we used PyTorch, and I actually like PyTorch a bit more. But you will see that most machine learning packages are pretty similar, and I think it's important to get related with all of them. Let's start creating our data. Remember that this partial differential equation is parameterized by these input functions u. So we need a lot of input functions to train our model. However, since defining each input function, let's say u1 equals to sine of x t, etc., for let's say 5,000 times would be pretty complicated, we will sample our functions from a zero-mean Gaussian process with an exponential quadratic kernel. And to do that, we will use some auxiliary functions. So please feel free to pause the video or remember that this code will be available in my GitHub. Okay, let's just start creating a single function, and then we can repeat the process if needed. First, observe that the input variables are x and t. So we will have some kind of mesh, and we will need to give it some kind of a structure. So let's set it to 100 steps in x, 100 steps in t. And also, please see that we need some kind of output sensors that are points inside our domain at which we will evaluate the solution of our partial differential equation. So let's call this a P train. I'll set it to 300. Nice. Now, before generating the data, let's enable double precision. You can see that this is pretty straightforward here in JAX. So it would be update in JAX enable 464 and true, and we're good. Now remember that we sample our functions from a zero-mean Gaussian process. So we need some kind of seed because we do this process randomly. So some kind of seed or key would be equal to random dot prng. Let's give it some another seed would be 0, and yeah. So now to generate the data, we will use one auxiliary function, which is an diffusion reaction numerical solver. This function will take some input parameters, will generate the random function, and then we'll plug it into the partial differential equation, and we'll solve it for that specific function. So let's use it. So it would be x t du, which would be the input function. Also, it gives us the input function evaluated at the output sensors or the p-train points. It gives us the y, which would be the points at which we evaluate our function, and also the solution of our partial differential equation evaluated at those points. So remember, this is like a solver for the diffusion, numerical solver for the diffusion reaction system. So it would be solve ADR, it takes t, the number of steps in x, the number of steps in t. It takes the number of the output sensor, which will be p-train, and also a length scale. This is used to generate the input functions. If you're curious of this, I encourage you to review the antiderivative tutorial. There we open that function a little bit to see how it works. Okay, so the length scale 3.2, and we are good to go. Yeah, now let's create some kind of mesh, which would be xx and tt equal to np mesh grid, and it takes x and also it takes t. And let's see if it works. And now, yeah, it works. So let's plot our function, which would be xx, tt, and uu. So let's see the function we are creating. So yeah, and please observe that if we change the key, let's set it to 100, we will get a different function, which is right here. Okay, let's choose some points from our initial and boundary conditions to evaluate our loss operator. And please remember that this loss function compares the output function of our operator when it takes u, evaluated at yu, against the solution of our partial differential equation when it takes u, evaluated at yu. That for this particular example, it equals 0. Now, let's see how to select the data. The first boundary condition would be when x equals to 0, and t equals to any number. The second boundary condition would be when x equals to 1 and t equals to any number. And the third boundary condition would be when t equals to 0 and x equals to any number. Now, please observe that y train or yu contains both x and t, and that these two variables, that in this case u train contains the u function evaluated at endpoints, and y train contains the p output sensors, are sent to the DeepONet to approximate to the solution of the partial differential equation. However, the solution of the partial differential equation evaluated at y train or yu should be equal to 0, and that is the condition that we are trying to enforce. Remember that the collocation points is where we evaluate our partial differential equation, and to do that, let's set the number of collocation points, say 100. Create a random index that contains u train items. Select the points from that index in X. Select the random numbers in T. Then collect both input variables into this YR train to be consistent with the previous names that we gave it. Now, you should see here that we have two UR train. And the question would be, are those the same? And the short answer would be no. It's the same input function, but they are evaluated at different points. And that's what we'll see right now. The last UR train is the one that we see right here in the last physics. So it's U evaluated at XR. So U evaluated at XR, so at the index that we defined in first place. But also in the lost physics, we have this r theta, and you can see that if we open this r theta, it depends on this g of theta, so it depends on the operator, and this operator takes u and takes y. So in other words, we use yr train, the first one, and ur train to obtain the operator, or to be a bit more specific, we use them to obtain the output of the operator when it takes u train evaluated at yr train. So, but if you recall from the previous part, usually the u train sets contains m points, while the y train sets contains p points, and p is not necessarily equal to m. So as you can see, those two variables are different. It's the same input function, but they are evaluated at different points. So as you should suggest, we should change the name here. The last thing before I forget, this style function, what it does is copy the vector many times. For example, in this case, it copy q train times, and in this case, copy p train times. Why do we need to do that? Because we need it to be compatible with the DeepONet structure that we will see in a few minutes. Okay, we need to generate 5,000 input functions to use as training data. And to do that, we will use this helper function that generates one training function at a time. So, okay, we need 5,000 functions, 5,000 points. Remember, we're working in a space and time, so we need some kind of grid. So let's set the number of steps for that grid. In the next, let's set it to 100. And if you observe closely, it's the number of points at which we will evaluate our function. So it's the same as m. Okay. So we will set that nx equals to m. Okay. The number of steps in time, we will also set it to 100. And the number of output sensors, 300. The collocation points, 100. The same as before. We need a random number. Remember, random dot prng key, and it takes 0. Actually, we need 5,000 numbers to generate the 5,000 functions. So to do that, we will set these keys. This will contain 5,000 numbers, and we will use this function called random that is split. And what it does is it takes a random seed, in this case the key, and from it generates in random numbers. In this case, would be 5,000. Okay, we should enable double precision, so it would be config update JAX enable 464. Set this to true, and here's where using JAX comes really handy, because JAX has this function called bmap that can take one function and evaluate it many times. So that way we can use this generate one training data to generate 5,000 functions in a single step. So we know what's the output. So it's all we have here. The only difference is that now we're going to obtain 5,000 of each one of those. So it would be bmap or vector mapping or something. Yeah, vector mapping, something like that. And it takes the function generate one training data. We need to set an axis. In this case, would be used the first axis. Yeah. And here we should give it the input variable. So we need a key, a p, and q. So your key would be the 5,000 random numbers. The p would be the p-train, number of output sensors, and the number of collocation points. And yeah, we should be good to go. Now we need to reshape the data to give it the right structure for the neural network. And to do that, we will call them, we will call them U boundary conditions. Remember that this first value, it's where we evaluate our operator. So it's our boundary conditions for this case. So let's call this U boundary conditions train. Let's first ensure that all of the numbers have the same structure. So let's give them to float 32. U train. This would be this vector. What was right here? Okay. Reshape. And what's the final shape? We want the number of functions times the number of output sensors, which would be train. And this -1 is in order to make the dimensions consistent. So it will do the same for everything else. So in this case would be y and s. In this case would be y and s. Remember, s is the solution of the partial differential equation. And we will do the same for the residual that we will evaluate the PD. So u res equals u r train. Y res equals to u y r train, and f or u. You remember we needed to u. F res equals f r train. Okay, once we reshape the data for the boundary conditions and for the collocation points, we do pretty much the same for the testing data. And now we generate 100 input functions. Well, one of the main differences here is that the random key should be different for the testing data than the random key that we used for the training data. Okay. Once we reshape the data, we should turn off the double precision, because otherwise the training process will take too much. Finally, you see that we create this function called data generator, and what it does is it takes your data set and, well, based on your batch size and some random number, it helps you split it. It makes your data set ready for the neural network. It's something pretty similar as what we have in PyTorch with the data loader function. So we set the batch size, and we send our data sets, or we apply our data generator to our data sets. Okay, so let's create a function to generate our neural networks, or branch and trunk neural networks. So you can see that this multi-layer perceptron takes the layers, which would be an array containing the structure of the neural network. We start by initializing them. So you can see that we use the colored initialization. We obtain the weights and the bias, and then we isolate the parameters. This function that here it's called apply is what we usually called in the previous tutorials forward. So you can see that for all layers except the last one, we apply the linear function, which would be w times x plus b. So and then we activate it using the activation function. And for the last layer, since this is pretty similar to a regression problem, you can see that we do not use an activation. We only apply the linear function. So it will be w times x, or the previous input, plus b. Okay. So now let's define our Physics Informed DeepONet. And to do that, we start initializing it, and we start initializing the branch network. And you can see that the branch network uses the function we just created. We give it some kind of a structure, and we use the hyperbolic tangent as an activation function. And we do the same for the trunk network. Then we initialize the parameters for both neural networks, and we store them into a single container called params. We define the optimizer, which we can see is the atom optimizer with exponential decay and a learning rate of 1 to the minus 3. These loggers are used to store the data. They'll store the loss functions. Okay, so now the operator net itself, you can see that it takes u x t, because that is what the operator should take. You can see it right here. It takes u and y, but y contains x and t. Okay, so you can see that exactly what I mentioned. Y stores x and t. B would be the branch network, and so we apply the branch network to or u. So we encode the input function exactly as we are stating we will do right here. Okay. We do the same for trunk network, but this time we encode y. Remember, y are the points at which we will evaluate the solution of our partial differential equation. And finally, the output of our operator net would be the dot product between the branch network and the trunk network. And that's exactly what we are doing here. Okay. Then let's define the loss functions. And to do that, we'll just start with the partial differential equation function. And you can see that the loss of the partial differential function depends on this residual. And this residual, it comes from the partial differential equation. So what we do is we obtain the solution of our remember, this would be the output function of our operator when it takes u evaluated at x and t. Okay, so it would be the solution of the operator. So we need that value, the first derivative with respect to t, and to do that we use the grad function. This is from the grad library, and you can see it takes the function, which would be s, and these are the input variables. So here it's the number 3 represents, because this would be the params would be the input 0. This would be input 1, input 2, input 3. So it would be s, the derivative of s respect to t, or to the third value. You can see the same for x, the derivative of s respect to the second value. So it would be 0, 1, 2. And to obtain the second derivative, remember all of this is obtained using automatic differentiation in the same way we did for the Physics Informed neural networks. So the second derivative respect to x would be, we apply 2 times grad. The first one would be respect to the second item, and in the second time would be for the second item once again. Why 2? Because remember, 0, 1, 2. Okay, then the residual would be what we have right here, that it's defined right here. Okay, so this would be s or ds dt evaluated at yr. Okay, yeah. So now to define the loss of the partial differential equation, or loss physics as we defined it before, the only thing we do is we get the batch, which would be the data from the collocation points. We select the input and output. U and y would be the input. That's what our operator takes. And then we predict the result. It would be the residual net of u, x, and t. Remember, y contains both variables. Then the final loss would be the L2 error between the output, that in this case is u, and what we predicted using the residual. So we are doing right with what we have here. Okay, so the output would be u, and this is the residual. Yeah. So for the loss of the boundary conditions, we do something pretty similar. We take the parameters and the batches from the boundary conditions. We isolate what is input and what is output. the inputs would be u and y. That's the input of the operator, and the output in this case is 0. Remember, because the solution of our partial differential equation evaluated at the initial boundary conditions is 0. So the only thing we do is we bmap. This bmap, remember, is a function that help us like evaluate everything in a single step of the operator net. When it takes u, y of 0, that is x, and y1, that is t. And then the loss would be the L2 error between 0 and what we predicted, okay? And finally, the total loss would be the loss of the boundary conditions plus the loss of the partial differential equation. Okay, let's define a function that lives inside our DeepONet to train your model. So the first thing we need to do is some way to make the step or how to modify our parameters. And to do that, we create this function called a step. You can see that the first thing we do is isolate the parameters. Then we compute the gradient of our loss function against our parameters. And after that, we update our model. It's something pretty similar as what we have in PyTorch for the backward and update functions. Okay, so now to the training process. So the first thing we do is we select the data. Then after that, we define the optimizer state, and how to modify the optimizer state would be with the step function. We isolate the parameters related to this state. We compute the loss function, and we store the loss function, or the 3 loss functions, for it to have some kind of register, and we print them. And also you can see right here that we have 2 functions that are also just in time. This means just in time. Then it's just a JAX function that helps us make the code a bit faster to predict S, which would be the solution of our partial differential equation. You can see it takes u and x. So it would be, so this function, what we would do this, g of u of y. And also to predict the residual, that it would be what we have from our partial differential equation. Okay, let's define the structure of our branch and trunk networks. And for that, we need 2 arrays. So it would be branch layers equals to, remember that the first value should be the number of points that go inside. So it would be m points. So it would be m. Let's make it 5 layers of 50 neurons per layer. But I think we have not defined m yet. So, but remember that in this case, m would be the number of time steps that we use to generate the data. So m should be equal to nx. That it was equals to 100 if I'm not. Let's do the same for the trunk network. So it would be trunk layers equals, in this case, the number of input variables would be 2 x and time. So it would be 2. I would also make it 5 layers of 50 neurons per layer. Okay. So now let's define our model, which is pretty straightforward. It's just the name we gave it to our network. It would be DeepONet, yeah, and it takes branch layers and trunk layers. Okay, so it would be DeepONet of branch layers and trunk layers. Yeah, we're good. We defined our model. Now let's train our model. Since we have already created a function to train our model, now it's right here. We just have to say model.train, and we should give it the data. So the first is the boundary conditions dataset that we defined a few minutes ago. That's right here. So it'd be boundary conditions dataset, and it also needs the residual or the PDE dataset that is defined right here. Race dataset. Yeah. And then we have to give it some kind of the number of iterations that for this case, let's use 40,000. Now let's start training. And I'll see you in a few minutes. Okay, so once we finish training, this is the total loss we get. But remember that the model performance could be improved if we explore some other network architectures, learning rates, optimizers, etc. But for now, let's see how the model works for our testing dataset. Remember that the testing dataset were 100 input functions sampled from a Gaussian process with an exponential quadratic kernel. To do that, the first thing we do is we extract the parameters from the model, and then we make the prediction. To make the prediction, we use this function called predict test that we defined a few minutes ago, and it takes y and u, and what it does is give us the solution of our operator when the input is u, evaluated at y. So this would be the solution of our partial differential equation. But since the input would be 100 input functions, this would be 100 output solutions. And that's exactly what we have here. This error S is the L2 error, or the relative error. So let's see how much we have here. So we have 0.7% for the 100 input functions, which is pretty good. But now let's visualize a single function, as it's a bit easier to do that. So let's say 100 function, the first function, let's give it one number, let's say 10. Let's see what we have. So this would be the solution of our partial differential equation for this function, for this first function, and this would be what we predict with our DeepONet, which is pretty close, okay? But what if we change the input function? Then we can do that just by modifying the seed. So if we have a different seed, we have a different input function, and we have a different solution for the partial differential equation, right? So let's give it to 230. We can explore other numbers if you think it's convenient. So you can see this function, it's a bit different, yeah. And the error would be 0.7%, which is pretty good. So now let's do this the last time. Let's say 23,000. Let's see what we get here. And yeah, so yeah, this would be the results. Remember that this partial differential equation was parameterized by u. So every time we change u, we change the solution. But we could also have made a DeepONet that is parameterized by the coefficients of this equation. Remember that this equation was parameterized by the diffusion coefficient and the reaction rate. And that would be all. Thank you so much for watching. And please, if you have time, review the author's website. Actually, I've obtained this example from their website, and here you may find a few other examples that could be useful if you're interested. Thank you so much for watching once again, and until the next time.